research at the Sony Corporation. He got his PhD from our math department about 3 years ago, and he's going to talk about enhancing accuracy and efficiency in diffusion models.
Yeah, thank you very much for being here, and thanks, Gilad, for inviting me. And I was doing PhD with Gilad, and graduated 3 years ago. Would you mind I turn off the lights a little bit? Or... Yeah, thank you. Wow, a little busy. Yeah. Yeah. Okay, so yeah, I'm Chieh-Hsin, Taiwanese, now working in Sony AI, which is based in Tokyo. I'm going to share about my research on different models, from its background into the advanced techniques. First, I'd like to introduce our collaborators. I mean, most of them are our team members plus intern and some external collaborator. Okay, so first part, I would like to introduce what is diffusion models, and then I will introduce several problems of diffusion model itself and about how we resolve that problems. Okay. So let me ask a question, have you ever heard of diffusion models or yourself are working on that?
Yes.
Pretty much, yes. Yeah, thank you. Nice. So I guess you may have some a basic knowledge about what the diffusion model is, or more general, what the deep generative model is. So what the deep generative model is we want to use neural network to learn to model this complicated data distribution. I mean, it could be an image, could be a audio data, could be whatever data. So the task of deep generative model is to use neural network to learn this data distribution. But for diffusion model, it is actually using this function, actually a vector field, to do the generation. So what this guy is called is the score function. It is a gradient log density, and it tells us how to move toward the high probability region of the data. So diffusion model itself is all about how to use this score function for generation. Right. I'm going to start from the history of diffusion model itself. It dated back to actually 2005-ish. And I will introduce step by step about the kind of development of the diffusion model until this point. All right. So as I mentioned, diffusion model or one track of a generative model is to use this score function for generation, and it tells us how to move toward the high density region. What I meant is we can literally move toward this velocity direction in the gradient ascent manner. And because this guy tells us how to move toward the high density region, so step by step updating, we can get the new samples if we initialize the random initialization. So here is an illustration that's originally we initialize randomly and then do this kind of movement step by step. This guy tells us how to move toward the high density region, and then eventually you will get the generation of the two Gaussian modes. But in practice, this guy is unknown. I mean, it is intractable. We don't have its information. So what we can do is to use neural network to approximate it. And this approximation is called score matching. We literally train the velocity field to match the score. Right. But if you look closer to it, in this objective function, we still have this intractable term, which involving the ground truth information of the score. So people play the tricks of integration by part to get rid of this score function. And they can just use this. They just need to know how to sample from the data distribution and train a neural network that in principle to match with this velocity field. All right. After this neural network is trained, how we do the generation or sampling, is replace this ground truth score with the neural network approximation one, and then run this process. Okay, so this is called the score matching, and how to use score matching for generation. However, like if you look closer to this objective function, like here is a trace of gradient part. So when the dimensionality is getting larger, this guy will be super expensive to compute. So how to get rid of this guy? A trick dated back to 2011 is to add tiny amount of noise on top of your data. And this noise is a Gaussian noise. After you perturb it, you are going to get closed form computation for the score of this perturbed density. It is simple, and because it is Gaussian, right? Okay, so once we computed this like a slightly perturbed density with sigma to be very small, I mean sigma is just the variance. What we can do is just replace this with the perturbed one. Then everything here is trackable, simply computed, and easy to run, right? Okay, this objective function is called the denoising score matching. We kind of add slight, I mean, we perturb slightly on top of the data, and then match the slightly perturbed score. And if the perturbation is small enough, then the newly obtained distribution will be approximately the same as the data. So I mean, there's nearly no difference. Okay, so still train the neural network to learn this trackable stuff. And after we learn it, how we sample is just replace the perturbed score function with the neural network approximated one, and then move toward the high density region. Okay, so this is called the denoising score matching. All right. However, there is still some problem. Like in the real data, the data itself may have different modes, and it contains high density region with some low density part. So if we just naively use the denoising score matching, like in practice, the approximation of the score function in the low density region will be super inaccurate. So how to deal with that? As back to 2019, like this group of people from Stanford proposed like a quite naive method to address this problem. Okay, so how they deal with this is they just prepare multiple labels of noises inject into your data distribution. And what the benefit of doing this is like okay, so if we prepare like multiple labels of noises, your training objective will just be changed from this one, which is one layer of noise, to multiple layers of noise, right? And because we have multiple layers of noise, we just like sum them up during the training for this approximation. Okay, so what's the benefit of doing this kind of preparing like an incremental multiple level of noises to perturb your data? As during sampling, during generation, at the first layer of noise, the most heavy layer of noise, we still run the longevity. We still move toward the high density like updates as I introduced, until a certain point that is almost converged. Then this one can provide a better initialization for the less noisy layer of sampling instead. And then now we run the with this like a better initialization, we run the sampling, the longevity way, moving toward the high density region with the score until a certain point that it converge. We use the like automatic point to serve as an initialization for the other, less noisy stage, and then run it, and then until it converges and do a multiple level of noises. So with this, they empirically found that, okay, this kind of multiple layers of noises can make the data estimation and the score estimation much accurate. Okay. So actually, the vibe of different model has appeared, right? To be more precisely, here I introduced like a multiple level of sorry. Okay. Here I introduce multiple level of noises and inject into your data distribution. But in principle, like if we prepare like infinitely many of noises like this, and in continuous time, it just becomes some like stochastic process. So, this is the high level idea of the different model. Like we prepare multiple level of noises, inject into our data as a for process. And we learn to do the reverse process, which is like for generation.
Can I ask you?
Yeah, please.
So like one thing that hasn't really settled in my understanding is that, so the time dimension of that stochastic process, what is the relationship between that and the Gaussian noise? Like, is there a direct relationship between
Yes, exactly.
Could you explain that?
Yeah, I'm going to explain.
Oh, okay.
Yeah,
Right.
yeah, they have, the continuous time process over here and the Gaussian process actually have a tight relationship, and I'm going to introduce. So at the high, let me like explain in the high level idea and then like boil down to the details. So different model at high level contains two processes. The first one is the forward process, which transfer from your clean data to pure white noise by injecting incremental amount of noise. Okay. And the second process is the backward process. In other words, is for generation, which gradually remove from a random noise to a clean generation. So it contains two processes. I'm going to explain these two processes in details and also answer your question. Okay, so about the forward process. It is a process bringing your data to pure noise. What happens in the middle is we perturb with a tiny amount of Gaussian noise, where the F and G are the noise schedulers that you can define by yourself. It could be anything. But the point is like we perturb the this level of data the noise copy of data with this like drifter, kind of shifting the pixels, and also the diffusion term, which tells us how to add the noise, the level of noise, to the next level of noisy data. So this is a for process. It tells us how to add noise. With F and G, noise scheduler could be defined by arbitrary. Just need to be fixed. All right, and if the time interval is like an infinitesimal, like small, then this one will just be a Brownian process. What it means is if we make the time step much finer, then this one will boil down to a stochastic differential equations, where the first one tells you how to move in your pixels, and the second one is telling you how to add noise. Okay, so here, I guess I can answer your question. Like the adding Gaussian noise is actually corresponding to this stochastic process of perturbation.
But here the delta T is very small.
Yeah.
Whereas your Gaussians have exponentially larger So like are those large variances added at each
Ye-
small time step? Or?
Yes, yes. So that is actually described by this term. I mean, it is a Brownian process with this level of variance that you add on top of your previous like copy of data.
But there is nothing physical about F and G, correct?
Yeah, there's nothing about it. It can be arbitrary.
Arbitrary, if I, what if I say it is 0 then?
Yeah, it could be. I mean, it couldn't be like it couldn't be both 0. I mean, if both 0, they just like steady. But it could be like any like a well-known process, say like OU process. You can choose the drift term to be 0, G to be like square root of 2, for example. I mean, it could be like any schedulers that you define. But there are certain like famous or like a well I mean common choose of the F and G. For example, we make the drift term to be 0 and the diffusion term to be square root of 2t. Yeah, it just like in practice it works well, and like yeah, people make this kind of choice. So in this case, the SDE gets you this format. I mean, just simple plugin. Okay, this is for process. For process tells us how to move from data to noise, and the F and G are predefined by ourselves. Now we just choose F0 G square root of 2t, but you can do anything that you want.
Question here. In your images, you're showing a cat there, correct? You have a cat image there. What is the eventual objective? I mean, I know you are translating it to somehow learning a distribution, but what distribution are you trying to learn from the cat image?
Yeah, so eventually we are still want to learn the clean the time 0 distribution, and I'm going to introduce how we learn it. So it's just like this is the for process about how to bring the data to noise, but how we do the generation is the backward process.
Yeah, but I want to understand what the objective is.
So just to clarify, it's not a single cat. He has several images of cats, and then he wants to generate a typical cat, like you kind of learn the distribution of his cat images.
Yeah, that's okay.
Yeah.
So there is a distribution that somehow captures the cat image amongst various images.
Yeah.
Okay.
So there are actually multiple level of distributions, clean, and any perturbed level of distributions. But what we want to learn is the clean one. Yeah. All right, that is about the backward process. So for this defined for process, mathematically you can ensure that there is a backward process that each level of distribution will be the same as the for process. And the format can be written down explicitly in this form, where we have the F as the for drift term, G as the Gaussian, the noising term. But here you can see that the score function appears. And now this one is the denoising term, where why I write the bar over here is just stating that we run from the reverse time process, like from the capital T, for example, to the 0, which is the reverse process of the forward one. Okay, this one, this SDE is mathematically ensured. They have the same distribution at each level as the forward one.
Jesse, I'm just curious, because the forward process, there's not much assumption, right? Because, even it generates some distribution, it doesn't mean we have the density function, right, technically. And also, even we have the density function may not be differentiable, logarithm in that may not be differentiable. So which kind of assumption or which kind of restriction we need to put on the F and the G to make sure that this happens?
That is actually a good question. So usually, technically people assume the F is sublinear in X, and G could be like a arbitrary. Just need to be smooth enough. Then it can ensure that this process would have the same marginal, the same like density as the forward one. And the kind of the strong solution exists and unique. So yeah. Okay, so like in our example, F0G is like square root of 2t. It boils down to this SDE, which is the backward process. Okay, so what's the point of saying this? What it means is like if we just randomly initialize some noise, then if we can have access to the score function at each level, we can just run this process backward in time for generation. So what does it mean? It's like the differential model generation is equivalent to the differential equation solving. All right, once we have the access to this. Okay, to be more precisely, so far so good? Good, okay. So like this is a stochastic process, like forward process is SDE, backward process is SDE, they follow the same marginal. And actually there is also a deterministic process which can follow the same marginal as the forward. What does it mean? It's like if we go from noise and this kind of denoising process, if we look in the middle, it has like a stochastic, deterministic process to tell us how to remove the noise from the noisy part to the clean part. It boils down to an ODE. If we look at the updates, like do some algebra and like take the limit. So this ODE and the backward SDE and the forward SDE will define the same slice of like a marginal at each time step. And eventually, when we do the sampling, what we need to do is just randomly initialize some noise and then like plug in this ODE, any solver. Then we can do the generation at the very clean, solving from capital T to 0, for example.
And where exactly is the PT/XT coming from?
Yeah, that is the point. So the field model is about how to learn this guy. Yeah. So this is just like repeating what I'm saying. Like we have the forward SDE, which tells us how to produce noise, produce data to noise, and it automatically corresponding to some backward SDE. And this process has like a deterministic process where everything here shares the same density. And the mass over here is, just like some PD, but I'm not going to dive into the detail at this moment. Anyway, so for different model generation, it's corresponding to, it's just equivalent to the ODE solving. And like to answer your question, like how to deal with this term is approximated by neural network, just as what we did for the like a score matching or denoting score matching. So if we look closer to what happened over here is like we train a neural network to approximate, like roughly this level of noise, this level of score. Here, the XT is just the perturbation. If we use our simple like example, like perturb X0 with T level of Gaussian noise. And this one, you can exactly compute it out because it is a Gaussian noise, so it has closed form. So once we train the neural network to approximate it, then we just need to replace the ground truth one with the neural network approximation. Then for generation, again, random sample some noise and then run the ODE, then you can get a new sample. So far, so good. So here I kind of summarize how we train neural, how we learn different model and how we do the generation. Training is simple, everything is computable. generation is also simple, where it just corresponding to ODE solving. Okay. However, there are several problems of different models. The first problem is about the training. Yeah.
I have a question. So you are training a neural network condition on X0.
Condition on XT, like the
But you're training it
this
to
one.
minimize
Yeah.
the score function condition on X0.
Yeah.
At some point though, you use it without the conditioning.
What you mean for the sampling?
Yeah.
Yeah, we don't use this.
So why?
Yeah, so this one, if you like just look at the one level of it, it's just the denoising score matching, right? You condition on your claim, which makes your score computable as this one, and then you learn this level of score function to approximate this condition score. Yeah, and if you, perfectly train your model, this one would not contain the X0 condition information. Yeah. Okay.
So you made the assumption that the fxt t is equals to 0, and here, and the slides is about score-based matching, but this formulation also looks very similar to the flow matching diffusion model, where this is considered as the velocity.
Yeah. So yeah, I actually don't want to touch this, but overall, because it's getting more complicated of like a different terminology. But overall, like the example I took here is just like the simple perturbation, like 1 for X0 and T for PT. But we can talk about more details later. Yeah. All right. So far, so good. Yeah, I guess I only have 30 minutes left, so I will just like chill and make sure that everybody can like follow. Okay. So there are several problems of different models. One is like a training inaccuracy. The other one is very slow for sampling. And the last one is scalability. I'm going to talk about each item step by step. For the inaccuracy of training, why it happens, I will explain later, but like we have work to kind of mitigate it. So why different model has the training inaccuracy is because your data is actually lying on the lower dimensional manifold. If you use your neural network to learn to do the score matching, this one is the score. The transition when t close to 0 will be super large because the score is kind of sinking toward this lower dimensional stuff. What does it mean is like the neural network may have hard time to approximate this highly non-Lipschitz function when time close to 0. So this may make the training of the score differential model inaccurate when time getting smaller. So this is one of the problems of differential model itself. Our work, which is called the FP-Diffusion, the FP means the focal point diffusion model, is trying to mitigate it. I guess I don't have enough time, so I will just like introduce the high level idea of this work. So, like as I explained until this point, like different model has a lot of mathematical underlying structure. The density, the particle movement, the XT movement is described by SDE and ODE, whatever. But the density itself also following some like dynamic structure, which is called the focal plane equation. The focal plane equation describes how the density evolves through time. Evolves through this kind of noisy copy. It is a partial differential equation. Like overall, like differential model itself has this kind of like underlying math structure. But if you like look closer, like how about the score function? Like whether the score does also have this kind of underlying structure. And the answer is yes. Like we found that for the score function, which is the gradient log density, with also following some partial differential equations. And if we impose this kind of underlying structure during your training, you can actually make your diffusion model more aligned with your more aligned with the physical structure or mathematical structure of the line behind it. So we impose this kind of TDE into the diffusion model training as a regularizor, and we found that the learned density could be improved. We show it mathematically that if you not only impose this PDE, but also train with your diffusion model's objective function, you can ensure your density will getting closer to the ground truth. I mean, I guess it's easier to look at some evidence. This is a true data density. This one is the vanilla diffusion model's learned density. But if we impose the underlying structure of the PDE, we can ensure that the density estimation is more accurate, more aligned with the truth. And same for other kind of data types like this. Yeah, I mean, I don't have enough time, so I just quickly go over this stuff. But overall, the first takeaway is diffusion model has many mathematical structure underlying behind it, and if we impose it during your training, it can make your model better. Yep. So good. Okay, the second one is actually the main research topic nowadays: how to make diffusion model sampling fast. And for this, let's step a little behind to see why diffusion model generation is slow. And I will introduce later that's how we make it fast. And this is our work. Okay, so why diffusion model generation is slow? It's because it's equivalent to solving ordinary differential equation. And if you recall your calculus course, solving differential equation, you are actually using tiny enough slopes to approximate your solution trajectory, which means you need to prepare a lot of slopes movement. And this is one of the reasons why it is slow, because you need to move step by step. However, if you naively do some this kind of long jump, eventually, naively, the quality will be terrible, because the approximation of the trajectory is not accurate, right? So for diffusion model itself, the slow generation is by its nature, because it is the same as ODE solving. And this becomes a trade-off between your sample quality and also the speed. If you prepare more steps for this, ODE solving, you can get more better quality, but it will be also slow, and vice versa. So it is a trade-off. Okay, so actually, based on this ODE solving perspective, it stimulates a lot of work to make diffusion model generation fast. One track is training free, that people just bring any sophisticated numerical solvers from math literature to improve the generation. It could be you use higher order information to approximate your gradient, or do some extrapolation to make the trajectory approximation even better. So there are tons of work to do this to borrow the numerical solver for fast sampling. Unfortunately, this research direction is ended because solvers are there. People already run off of the solvers. All right. The other one is training based. It includes two different directions. The first one is how to make your diffusion generation trajectory more optimal for sampling. What I meant is like, say, for example, if we can make this trajectory sampling trajectory like more straight, then you can use fewer steps for solver to solve to do the generation or like solve the ODE. It includes some famous work from other like a research lab, but I'm not going to talk about this in details. The one I'm going to focus on is how to use pre-trained diffusion models and distill the generation steps to fewer steps with some pseudo model. So I call it as a distillation-based method. And this one is one of the mainstreams of nowadays diffusion model research, like how to make diffusion model fast by distilling the pre-trained diffusion models.
For the training phase one, the middle one,
Yeah.
what are those two trajectories? Is it assumed that there's a generative process which generates cat images, like the ground truth?
Yes.
Trajectory? So what is that one?
Yeah. So for the middle, for this one, it just like a.
Oh, I meant the two, because it's kind of a big assumption, right? That there's the ground truth generation,
What do you mean here?
like those two wiggly black ones. What is that trajectory?
Oh, sorry. This is the distribution.
Oh, it's a
Yeah,
distribution.
sorry.
Okay,
I mean,
okay,
this
I'm
is
sorry.
let me see.
So there's no, okay, like because I think a lot about like the time things. So this is from one stationary distribution. to
Yeah,
another
it's just
station. It's not
stationary, yeah.
from okay, somehow I thought that they were just like.
Yeah, I guess the color is not
All right,
so
now I
distinguishable.
understand, just all met. Thank you, sorry.
Yeah, thanks. Okay, so I'm going to focus on the distillation-based stuff. How to, distill your pre-trained diffusion models, sampling steps, which takes originally like 1,000 steps, into fewer steps, say 1 or 2 steps. Okay. So the idea is actually very simple. Like, essentially, like diffusion model generation is equivalent to ODE solving, right? We call the solver and then plug in the solver for generation. So the idea of the decision-based method is like, we kind of bring this solving in the sampling and in the inference step to the training. In other words, we directly use the neural network to learn this solver with one step. So what does it mean is like, with a pre-trained diffusion model, we call it as a teacher model, and we run the solver from any initialization till the very end, which produce the generation. Then we have a student model, which take the same initial condition and learn to match at the clean. Sounds good? So during the, yeah.
In theory, if we have an X target, in this case, don't we just have the training data still? Or like, if all we're doing is trying to match the target, why do we need the teacher in this case? What is it specifically bringing?
Yeah, so the why we need to have teacher is because like in principle we do not know the true sampling trajectory starting from any initial condition. So we need to use the teacher to approximate it. Yeah. Okay, so the distillation-based method is simple. Like we just let's assume like we have a teacher and we want to make the teacher sampling step to, extract the teacher sampling to the student. And the way how they do it is like, for a teacher, during training, they just run the ODE solvers to get a very clean generation. And the neural network is trying to match that target with one function evaluation by plugging the initial condition xt. So the training objective is simple, like you just match these two data points with any distance. Yeah.
So to clarify, you are training a new neural network.
Yes. The F neural network, which is a student neural network. Okay. But there are some problems. The first one is it's kind of a little bit cheating, right? because we kind of bring the same inference, like a slow inference to the training, and it can even cost the training even more expensive. Another one is like, because different model has this kind of any to zero, different model has this kind of progressive generations stuff. So we can actually control the middle part for flexibility, for controllable generation. But if we do this kind of one long jump of the solver, then it kind of misses that controllability. So how to like kind of balance these two? I mean, how to resolve these two problems? It's the issue. So our work is trying to bring up a method that can not only make the sampling fast, but also you have some certain of controllability of generation. Okay. I guess I only have 15 minutes, but yeah. So our model is called the CTM, Consistency Trajectory Models. Let me first introduce the training mechanism and then talk about what's the benefit for sampling based on our model. So our CTM model is actually very, still straightforward. The idea is straightforward. That is, we want to learn any to any time jump from any starting point T to endpoint S. So how we do that? Like in principle, we want to learn this kind of solver, which do this kind of T to S jump. With if we have the ground truth, then we can do this kind of jump. But if not, we use the teacher model to approximate it, where we call the solver. So our neural network is trying to take the initial condition xt, and then take the initial time t and jump to the end time s. This student network is trying to match with the solver output. However, still, like because the s and t are random, if the s is going to the very end of 0, then you need to still call the solver till the very end. So we still have the expensive problem. How we mitigate this is, instead of like solving until the very end s point, we randomly stop at the u. And for the u to t interval, here is where we match, where we call the solver. So for the training target, what you do is like starting from any initial time, call the solver to solve it to the random middle u point. And then we call the student model to take this initial condition and output the endpoint at S. This creates the training target. And this point need to match with directly jump from xt to the S point. So we impose any loss function over here to match this output trajectory and this one. Okay, so the high level idea behind this is like, for ODE, once you initialize the same initial condition, then the trajectory will be the same, no matter where you start your ODE solving. Okay, so that's good. So in principle, because the start point, the start time, and end time are arbitrary, so we can learn how to do the anytime to anytime jump movement. Okay, I'm going to skip a little bit, but overall, like we can do the anytime to anytime jump along the trajectory. For sampling, once we train this model, what's the benefit of sampling? Is that it contains two extreme cases. The first one is if the end time is far away from your starting time, you can do one long jump. You can do the fast sampling. But if the end time is very close to the starting time, then it actually recovers the score function, the slope information. So, which means with this unified model, the CTA model, by choosing the end time or starting time, depends on your preference for sampling, you can recover the fast sampling distillation-based method and also the original diffusion model sampling. So also good?
But isn't this because you are making the problem more general and therefore more difficult? Like, is there a training trick or something that allows you to first learn the little?
Yeah, there are
Okay.
several tricks, yeah. Like,
Because otherwise this problem is a generalized version of the previous problem, right? Like
Yes.
you want to go from anywhere to anywhere.
yes, yes. Yes.
So what's the trick? Will you tell us?
Yeah, so for the trick is like we need to like make parameterization of the neural network to follow certain solvers form so that we can have some fixed target, fixed initial condition, and then just learn the rest of the integral part. So it has some certain like format of the parameterization, but it is mathematically reasonable. So yeah, so like overall, like the CDM models can provide you fast sampling if you do a long jump. And also it can provide you the diffusion model sampling if you set your time step like incremental. Okay. So it is a unified model between the like distillation-based method and also the diffusion model itself. So let me put into details, like for one-step generation, all you need to do is like random initialize some noise and plug into the initial time t. And then the end time is 0. Then you can produce some like a generated image with one step. If we compare to the teacher model, the time difference is perhaps you need to take a minute to generate this one by calling the solvers with 79 steps, for example. But with our model, you just need within a second to generate like quite great data. So that is actually a huge improvement in terms of the sampling time. Okay. And yeah, I guess I don't have enough time, but because we know, the model learns how to do the anytime to anytime movement. So we actually can have more flexible sampler. And we call it as the gamma sampling. What does it mean? It's like the gamma here control the stochasticity of the generation that you want to throw in. At one extreme is gamma equals 0, which is corresponding to the fully deterministic sampler. What we do is like during sampling, you prepare some time step, and you just move this kind of time stepping manner for generation. It's similar to the different model, like removing the noise. But the entire process is deterministic. All right. One of the extreme, so this is one is the deterministic sampling. And we actually can know what would be the deviation of the resulting distribution from the ground truth data. At most, it is just like the old capital T, where capital T is the sampling, total sampling step you choose. At one extreme is gamma equals 1, which is fully stochastic sampler, where you jump one long step to the vertically, and then perturb noise back to the middle, and then do long jump, and then perturb to the middle, long jump to the middle, and long jump. So like you can use this kind of stochastic sampler to make your generation more diverse. Because we have this kind of perturbation to the middle, by adding noise process. So again, extreme case of the deviation from the resulting distribution with your ground truth, at most it will be deviated at this amount of error or discrepancy. Okay, and in the gamma, for gamma in the between, I guess you can somehow imagine that we can do certain interpolation. So what I meant is like, we denoising to the 1 minus gamma level of noise, and then perturb it, and then do long jump to the certain, the less noisy level, but scale with 1 minus gamma square root, and then perturb it back and do this kind of backward force process. But overall, you can have a more unified way to sampling, with the middle of gamma. The deviation is like a kind of complicated, but if you look at the extreme case where gamma equals 0, it just goes to the capital T. But if gamma is 1, then it just go to the accumulation of all the sampling step. Anyway, what's the purpose of doing this? So with the gamma sampling, you can actually control how many diversity you want to throw into your generation. Here I'm going to play some sound clips that is trained on top of trained with our model and generated with our model. So the first audio I'm going to play, actually the sound is one-step generation of the sound effect. And the generation should be matched with the user specified text prompt, sound claps and some rainfalls, this kind of stuff. You can be aware of the timing of the sound claps. All right, so this is one step. Okay. And now I'm going to play, oh, sorry. Yeah, I'm going to play gamma equals 0, which you can observe that the semantic meaning will be nearly the same as one step. Let me do it again, sorry. Happens over here, you can see from the spectrogram, the Fourier transform of the stuff. But if we do the gamma equals 1, which is fully stochastic, I guess you can notice the generation is semantically varying from the one step and also this deterministic one. I'm going to play it. Hey, so with the gamma sampling or our model, the gamma sampling of CTN features, we can do this kind of flexibility for generation. So what we can use it for? For example, if user want to control certain part of the generation to keep it the same, then they can just choose the gamma equals 1, gamma equals 0 for generations. If user want to have varied generation, for different contents, then they can choose gamma equals 1. And this will be super helpful for the music production. People can have different purpose for different sampling. Yeah.
So I know if you start from the same noise and following the same deterministic ODE, you will always be the same output, right? And you are kind of just allow some stochastic in this backward process.
Yeah.
That will make the generated sample more diverse. But how can you know when you're adjusting the gammas here, it actually has something to do with your text prompt, for instance. I felt like it's just making the generated sample more diverse. But how do you have a way to quantify the controllability, based on the text input and how the generated audio has something to do with the text input?
So for the text input, it is all fixed across all fixed across here different gammas. The short answer is there's no good quantitative way to quantize, to measure how diverse your sample or deviates from your original one. Naive way you can do the L2 descent, between the spectrogram, but it is not so meaningful. So for this kind of diversity, people usually use the people evaluation. So that's one of the ways. Yeah, so I guess I don't have enough time to cover all of the stuff. Sorry. Yeah, but let me briefly summarize it. Like we have another work which is making the diffusion model more scalable across different resolutions. The point is like because the diffusion model generation is equivalent to solving ODE, right? And the ODE solving need to stay at the same resolution. If you want to generate higher dimensional data, you need to retrain your entire diffusion model again at the higher resolution one, which is super expensive. Plus, if you want to do the distillation tricks, you need to first train train high resolution diffusion model, and then train the distillation stuff on top of that. So there are two-stage procedures, which are extremely expensive and tedious. So our work, which will be presented at NeurIPS this year, is how to make the entire pipeline efficient in terms of training and also for sampling across different dimensionality. So I'm not going to talk about this, but let me just skip it. I mean, if you are interested, we can have discussion at the end. My point, kind of a closing remark is like, for different models, it not only is useful for pure generation, but it can also be applied to like inverse problem solving, and also like many wide range of tasks, say like make your generation more controllable. And you can also do the discriminated task, like do the classification, whatever, anomaly detections. So actually, there are lots of research stuff you can think about how to use diffusion model or how to improve it. And yeah, that will be the end of my my sharing. So thank you very much.
Jesse, if anyone needs to leave to classes, you can leave now and we can continue with questions. Exactly, I'm curious, you know, you had different values of gammas. Did you get them on real applications for Sony?
Yeah, I mean, there are some people like engineer try with that for like,
music application?
Yeah, for music application.
So
yeah.
How do they, you know, what's the conclusion so far, you know, about the best values of gamma?
Yeah, so actually for it depends on the purpose. Like if you want to make your generation at high quality, gamma equals 1, which is the deterministic one, will be the best. But if you want to have certain diversity, then you can choose small gamma, which kind of balance your quality and also like have several variants. And like the why we need variance is just because like for some music production scenario, we want to create, say like a footstep. I mean, the sound of footstep. We want to create several variants of it for different situations, say like movie situations. So yeah, I mean, it really depends on the applications.
So they use it actually for generating kind of different sound effects.
Yeah.
Right?
Yeah.
But do they also use it for real music generation or?
At this stage, no. Yeah. Yeah.
Any other questions?
So I have a question. So like for the ODE solvings, when we're using neural networks to approximate the solver, have you tried using the surrogate models? That is, so it's like well in mechanics they have operator learnings, so they will have like pins and Fourier neural operator, that kind of stuff. That is kind of like we can learn the equations and have the solutions at any of times. And so have you ever tried to using them to solve the problems? And also I know the Fourier neural operators is kind of resolution invariance, so they could have a much higher resolutions even if the training is based on low resolution data.
Yeah, I think the difference is like for the I mean the ODE solving or the ODE learning stuff is different from the pins or whatever is because it is unsupervised. We only have the noise. I mean clean data and the perturbed version. But for pins or like a neural ODE, neural operator learning, you need to have supervised information. So, but essentially they are, I mean, they nearly the same. I mean, we just use the pre-trained model to approximate the solution. But in pins, it's just like grab the two endpoint for them. So
I got you. Thank you.
and actually, our CTM is based on OpenAI, one of the OpenAI's paper, which is called the consistency model. We improve it and make it more like flexible for different purpose. So, yeah.
Thank you.
Yeah, thanks.
So pins and you know, many pins. Actually, is it popular in your group also?
Pins?
Yeah.
I actually know, but I'm interested in that. Yeah.
And what about neural operators?
Yeah, I'm interested in that, but they are, I mean, in our group, they care less about the scientific, I mean, AI for science stuff.
I know we are running out of time, but could you give a high-level summary of your last line of work for high dimensional diffusion? Because to train a diffusion model for high dimensional data, the demand of the size of the training data set is usually large. Right?
Yes.
So
Yeah, the TLDR for the last work is like we just need to have a low resolution diffusion model, pre-trained low resolution diffusion model for almost like resolution agnostic generation. So the high level idea is like we downsample the high resolution high dimensional data to the low resolution one. And here is diffusion model is trained. After it's trained, we run the ODE solver from the clean to noise. It is different from the previous one I introduced for distillation. Like in the distillation based method is from the noise to clean, but here we run from data to noise. The purpose is to creating some meaningful like a semantic latent, and just follow some like autoencoder structure, like you decode it and match with this. Why we want to do that is because you can like when you downsample it and do the decoding, I mean learn the decoder at the low resolution one, after it train, you can gradually add additional layers, trainable layers on top of your trained decoder to do the super resolution. And then you can match the higher resolution over here. And then after you train, you can add additional layers to do the even higher resolution matching. So it's more like a progressive manner of the super resolution generation. Yep.
This is to kind of deal with a manifold structure.
Yeah, it could be, yeah.
Or what do you gain by adding because the standard, super resolution architecture is just this without the intermediate diffusion, right? So what do you gain by, can you sample different images or what's the advantage of having the diffusion and development?
Yeah, to answer this, our trained model still doing the generation, which means we still randomly sample a noise and at the low resolution and do the decoder one step to produce the sample. And why we need to have the diffusion model over here to plays a role as encoder is because we are still doing certain distillation. Here, the distillation, I mean, this diffusion model ODE solving plays a role as the teacher model, but now it's starting from the.
So there's like a pre-trained.
Yes, yeah, over here is pre-trained, yeah. And actually with this, we have certain guarantees that the optimal solution will be the ground truth data. And also we add some gain to make it generation much better. And we can ensure that the gain training with this kind of fixed different model autoencoder will be will be stable.
So someone at home asked if you're going to share the slides.
Yeah, I can share the PDF.
Any last question?
So I have a very dumb question. I'm new to this. So I didn't get the difference between like when you give the model a prompt and you set the gamma as 0. And then the second experiment is you use the same prompt but set the gamma as 1. Is there a third experiment that you use a different prompt, but you set the gamma as 0 and you can get the same result as the second experiment? So I didn't get, because so sorry, let me organize my question. So is by the method of setting different gamma, is it like controllable? Like can you predict the variance of the result? If it's not predictable, then how could you efficiently leverage this, like this technique to generate something you want?
I guess you are talking about if we vary the text prompt.
Yeah.
Yeah.
Because you showed some audio output. I'm just curious why don't we just use different prompt to?
Yeah, like for the prompt, like there's less information you can make the control because how you describe like the result. It's not the way from here, but how you describe the like we want to have thunderclaps at this timing and the other timing. It is hard because the text information or text embedding is not so well studied or like well established. So doing the text variant could be possible, but you somehow like don't know the full information of that. Yeah. So you can like there are two options. One is do the text prompt modification, and also you can do the gamma stuff. But the gamma is more controllable because you can really adjust like how many noise you want to add in.
Okay.
Like, okay, simple example like text prompt, like say thunderclaps, and say I want to have the thunderclaps at time 3, for example. The embedding of this this text prompt may not be the same location. Nearby locations in the embedding steps. So for the text embedding or the text information, it is much harder to control, to understand. Yeah, thanks.
Yeah, thank you. So next we have discussions with students. Anyone can join, but it's mainly about advice for students. The next half an hour, so please don't take just his time at the table because he needs to talk to a student.
Thank you for being here.
Yeah. Safe travels. Nice to meet you.
Yeah, thank you.
On the
We're not sure about that.
so we know the EDM paper also point out that when doing the backward process, when the time set is close to 0,
Much easier to train
that range of the reverse process tends to be more unstable. So do you think some
Do you do much with diffusion models?
I think it's just 3 times.
Or you may, or using ODE for the most time, but for some very unstable density
okay,
as
yeah, that could be.
estimation region, use SDE. Just hope that the noise can do in some error correction.
Yeah, I think there are several works
So
or.
I prefer start with question, so.
Okay.
So if you're a student, you don't pay.
Like I know it exists, that's the limit of it.